Over the past 100 years or so, a premium steel has been developed. It's called tool steels, and these are used to make machines and special products that are used mainly in manufacturing. These steels vary, but they all have the same characteristics. They're too expensive to use for making consumer products and structures. They are used for things like dies, punches, knives, molds, reamers, saws, in mills. They're used as their name implies, in tools. This slide shows some figures of steel when you're tempering the steel. Now, tempering is when you warm the steel, make the steel very, very hot, and then you allow it to cool. And as you can see, the hardness as the temperature testing temperature rises, it drops. And you have this problem sometime with drills and lathe, the cutting bits on lathes. So you have to keep this in mind with steel. And generally, a good idea not to run the tool to it's too hot because of the change in the chemical structure of the particular tool. Wear resistance is sort of self-explanatory. It's how long this piece of tool steel is going to last in the job that you have for it to do. Now, it is really sort of subjective in that all vendors are going to claim just how good their tools are with respect to wear. By trying some different ones, you're going to find the ones that actually are going to give you the best wear for your particular application. One of the correlations of how well the tool will wear is the toughness test. In other words, how much the battering and abuse the tool can take before it breaks. Because generally with tool steels, you're going to have a break. They're brittle, and you're going to have some sort of break that's going to be your problem. Here's an example of some different findings on different steels as far as their toughness is concerned. Of course, with the more toughness you have, the better the tool steel should last in your application. As you have surmised at this part, the selection of tool steels is really a trade-off. A trade-off of different things that you want to try to achieve to find your best fit. Now, this particular table gives you different types of tool steel and some of the pros and cons of that steel with respect to toughness and wear and depth of hardening, etc. This is a useful table in that you'll find a sort of a balance, a trade-off of exactly what you would probably need for your particular application. Another view of this tool selection is shown here in this particular figure. As you can see, depending on what you want to do, whether you want toughness or whether you want hardness. For instance, hardness. Your cemented carbide is going to be the hardest, but is it very tough? No, it's not very tough at all. So if you bang this thing around very much, it's not going to work very well. So you have, once again, you can kind of see a trade-off of the different characteristics of the different steels in this particular figure. And as you can see on the right hand side, the cost and the results are shown as far as what's the best and what costs the most, etc. This slide shows a comparison of tool life based on turning a AISI 1020 steel part. And as you can see, the T15 is going to be the best. It's going to give you 55 minutes of tool life. Still, the price of the operation, it might be better to run the M2, which only lasts 30 minutes. They may be much less than half price, and when you factor in the cost of the operator changing the tools out, that may be a more economical route for you to take. In addition to tool life, you can also look at wear, how quickly a product wears, and here you can see some wear rates in cubic centimeters per minute And once again, you can see different tool steels and how quickly or slowly they wear. As we mentioned earlier, there's about 70 tool steels in the United States, although a smaller subset is actually currently in use. Really, you could break that subset down even smaller. Here's a list of about 12 different tool materials that you could use. These are probably going to cover most of the things that you're going to run into. The first 7 are tool steels. The bottom ones are not tool steels, but ones that are quite often used. Depending on what you're looking for, these are going to be good selections for you in your manufacturing processes. Here's some other characteristics to keep in mind when you're selecting your tool steels. The first one is wear properties. Generally, the harder the steel, the better it will be as far as wear. Now, if two steels have the same hardness and one contains a significant concentration of carbides and the other has none, then the first one will have the greater abrasion resistance. In other words, the one with most carbides will have the greatest abrasion resistance. Another thing that's very important in working with steels is the machinability. That is, how well this steel will work. This is really sort of related to the cost down at the bottom. The best ratings for working steel are the O1 steel, tool steel, and the cost of this machining this steel would still be about twice the cost of a standard steel, like a 1112, 1112 sulfurized steel. In other words, it costs $1 to make a part from a 1112 steel. It would cost you $2 to produce that same part from an O1. The cost, if you were going to make it out of something like an A11, would be about $8. And if you're going to make it from other cemented carbides, then it would be even more expensive than that. The thing dealing below, the next item you have is a thing called working hardness. And what we're referring to in working hardness is if two particular steels are rubbing against one another in a sliding manner. What you want to do there is to actually make both of them the same hardness. There is some thought, which is incorrect by the way, that you make the one hard that's expensive and the one that is not as expensive, you want to go ahead and let it wear out, is less hard. That's generally not a smart thing to do. If you want to try to follow that theory of thinking where you want something to last and the other part to wear out, then the mating member should be made from a good grade of bronze or cast iron with good lubrication, or maybe some kind of self-lubricating plastic. Generally though, you'll be better to just go ahead and make both of these mating parts the same hardness and lubricate them well. Let's look at weldability from a designer consideration. Weldability should be avoided on tool steel. Some things can almost not be welded. Cemented carbides cannot be welded by any conventional means. Some tool steels are almost impossible to weld, such as a D2 or an A11. As stated, the best practice is just to not weld tool steels. And of course, never design a product where you need to weld a couple of tool steels together. That's going to make a lot of scrap. You're going to have a lot of cracks where these things weld. If you must weld a tool steel, what you need to do is you need to bring it to an anneal condition. In other words, heat the steel, do the welding, and then slowly cool the steel, and then re-anneal it again. Always remember though, even doing this with the tool steel will have a weak point, probably where the weld is made. Just as quenching the steel tends to make it harder, quenching being to elevate the temperature of the steel and then dash it in water, dash it in oil. You can also anneal it, which means you raise the temperature of the steel and let it slowly cool. And by doing this, you'll actually make the steel not as hard as it was once before, so you can actually make it softer. Now, still though, you have limits to what you can do. Here's an example of one of the hardness. If you anneal this steel and you use a temperature, let's say between 400 and 600, then you're going to have a Rockwell C hardness between something like 62 and maybe 57. Now, if you wanted to make it not quite as hard, you can move over here into the 1000 and 1200 degree range. But see, if you're not careful here, though, you're going to make it very, very soft. If you slide over here at the 1200, you're down in the Rockwell C hardness of about 42 or something like that. Another characteristic about the tool steels is that that sharp corners tend to crack, so you want to avoid sharp corners. Now, this particular table that you're viewing here in table 15-5, it gives you an allowance as the curvature that you need on these corners so they won't crack. And these tables are valuable in your design. Just remember, you don't want to have sharp corners because they will be places where you'll have stresses and your steel most likely will crack. Here's some parts that may require stress relieving. As we mentioned a minute ago, avoid these sharp edges. Another thing to think about, which you don't sometimes think about, is sometimes people stamp numbers on their parts with metal stamps with dies. These will make sharp corners also, and can be a place of weakness in your final part. This slide shows some cracks where these sharp corners are. And as you can see, these are examples of crack-sensitive shapes. As we mentioned a minute ago, you need to round these sharp corners so you won't have that possibility. With this slide, we conclude this chapter.